Everyone, welcome to this QS Sedgwick Club talk. Tonight we have Professor John Bridges talking about the Curiosity rover mission. Curiosity has been exploring Gale Crater on Mars since 2012, and John is a participating scientist in this mission. John is Professor of Planetary Science at the University of Leicester. His research focuses on the Martian lithosphere, including water rock reactions in the crust, and he also looks at some mineralogy of primitive meteorites. And with that, I'll hand over to you.
Thank you very much. Thank you very much to the Sedgwick and yeah. So, but I didn't need too much persuading because, to be honest, I enjoy talking about exploring Mars. I'm very glad to be part of the Mars Science Return, and I hope to persuade you in the next 45 minutes, hour or so, that we've made some really useful sort of discovery. So there are some of my collaborators and all sorts of people from all over the world, engineering and science teams, who just have to get together to make the Mars rover work. And so I'll give a flavour of what it's like to work on operations. And we're up to 4,075 solid Martian. So 12 years. So if you had told me right at the beginning on landing night that I'd be still working on this mission after 12 years, I would be pleasantly surprised. But it has been surprisingly durable. Okay, so let's see if I can work out how to proceed move the slide. Yeah. I think I might have to stop sharing. So, oh, no, that's good. Right. Okay, so I'm going to talk a bit about Gale strategically that we've been piecing together, and why we went to Gale in the first place, how we selected from other contenders. I'll talk a bit about the mineralogy and the water rock reactions in the Gale sediments and what some of the idea about what that tells us about Mars environment. Some are discoveries, some well established, some still controversial. Controversy is never far away in Mars science, and that's part of the reason it's fun. Some of my work on igneous rocks and meteorite context. So hopefully there's something for everyone here tonight. And also, okay, but let's go back to 1957. All the associations. So we've been here. If I'm sure there were talks in the Sedgwick in 1957 about Mars. But if you wanted to look it up, of course, it didn't have Wikipedia, but the Wikipedia of the day was the Encyclopedia of the Time, which had the aim of capturing all useful, relevant information in the world. So if you look up Mars, you'll see this is the sort of state-of-the-art Mars imagery. So, you can see it's the seasonality, which is such a strong feature of Mars, is there, and these dark patches. And at about that time, if you look up the textbooks as well, and sort of stuff about where these dark patches, vegetation, lichen, etc. So it's not so very, that it was pretty much commonplace idea that yes, there was life on Mars. There's been sort of ups and downs in the life on Mars and life in the solar system story since then. Okay, fast forward a little bit to the first Marin Fall, and this grainy video images coming back, and about 1 kilometer per pixel. So if we're looking down on Cambridge with the camera about 1 kilometer per pixel, then you could probably just about work out that we were in some sort of urban centre, something like that. So the story that Mars Science Laboratory fits into is how we've got increasingly powerful, high resolution types of data, both visual, spectroscopic, and tied in with engineering progress as well. So when you think back in 1964, you know, must have been great if you were working on that camera, but maybe for quite was a little bit disappointing, you know, where were the lakes, where was the vegetation? It's very lunar, doesn't it? Because you must never forget that your view of Mars changes every time you get a different resolution, different spectral panel, etc. Today, so through the 1960s, the Mars into Viking became established that Mars today is cold and dry, though with seasonal variations, but the average pressure is about just 10 pascals of CO2. So was that the story of water on Mars, which has been, you know, stimulating astronomers since the very first telescopes back in the 17th century, or was there more to come? Well, there was more to come. So here, circa 1976 to 1982, the classic Viking 1 mosaic. So you see this all over the internet book. This is the western hemisphere of Mars, with the fastest consuming volcanoes on the left, Palus Marineris in the center of the view. The resolution here was sort of tens of meters per pixel. So if you're looking down on us now, pixel, we work out that we were in some sort of cluster building or something like that. So the view of Mars. Okay, so leading up to this, two landers, two identical landers, two identical orbiters, and Jupiter, real Cold War technology, just to make sure it worked, and NASA beat to it. But we didn't have an accurate atmospheric composition, and we didn't really know what it was made of. We know from petrological theory that if you take your chondritic starting planetary embryo, and basically you have a bit of convection, then you're going to produce in the mantle, then you're going to produce basalts. And we see this ubiquitously in the surface of the rocky moons of the terrestrial planets. So the sort of starting null hypothesis was that Mars was just a big lump of basalt at this point in time. Okay, so we started having successful landing missions. This was 1976. This one is Viking 2. And Viking 1, although we think this is impacted yet, now Viking 1 and the next mission in 1997 actually said, look rather like this. And when you see images in, you know, popular media, cartoons, whatever, of an alien body of Mars, you know, you've got that reddish, gently rolling terrain with a few rocks on it. You know, that's from this sort of era, that view of Mars. But it was very, very limited view because there were only a few places we could land, and the resolution of the imagery and spectroscopy was very limited. And these were interpreted as rocks from floods and impact ejecta, which were lumps of basalt. So, what's the story of Mars now? A lump of basalt and an occasional flood coming off the ancient highlands. So that was the sort of paradigm, if you like, circa 1976. Except hiding away in some of the slightly higher Viking imagery, there were these interesting images. So these channels within parts of the ancient highlands were striking. I mean, what formed them? So there's almost a sort of reluctance to go to the sort of the big picture conclusion that these were formed by water. So for many years, people were arguing strongly that these were likely to be formed by liquid CO2, because you can drop liquid CO2 pressure temperature conditions, or perhaps even lava channels. And that sort of debate has been going on even right up to the beginning of the Mars Science Laboratory mission. But the most obvious explanation is that they are relics of a hydrological cycle. Even if it's a sort of simple grainy image like that would infer that you've got some sort of aquifer, some sort of surface water flow, and it's going down to some sort of a large lake or down the bottom of water, perhaps with evaporation, a larger network, and then some sort of cycling with clouds. So trapped within these images, or recorded in these images, was this tantalizing glimpse of a different Mars, a warm and wet Mars, as opposed to today's dry Mars. So how have we come to that? Warm and wet before Mars. Okay, fast forward again. Modern imagery. So we have high Mars camera since 2006, which I'm a co-investigator on, which is 30 centimeters per pixel. So if we're looking down on us here today at 30 centimeters per pixel, we could probably work out that we were in some sort of maybe not lecture theatre, but within some sort of grouping of people within a particular building, something like that. So you can resolve objects meters across, including Mars landers. So here's a really important one. So here's a relic of called Edison, and we very nearly selected this for Mars before we did. Just picked on post by Gale. It's always tantalizing. You should wonder what would happen, what would it be like if we'd gone here. It's by analogy, and I'll use the word analogs a lot of times. The irony of going to another planetary body is that almost the first thing you've got to do is look back on Earth and see how those features that you've just identified on the planet how they form and what you life into it is by comparing to something back on Earth. So that's part of the really sort of refreshing way, a part of space exploration. It's another way of bringing in sort of terrestrial, geological, and other expertise. Okay, so deltas, we've got these fingers, these anastomosing channels of bars of sediment deposited, and these can only have formed by some river flowing into a large standing body of water and depositing. There's also spectroscopic evidence of flow, or a little bit about that later, but this really is part of the key, one of the sort of key images, if you like, for the ancient warm and wet Mars. So by the time we were getting these images, we realized, no, Mars isn't just a pile of assets. Okay, so that's the reason we wanted to go back, because we realized with the new images that it was worth going back with the point of stopping off in the 1970s and 1997. So here's my ticket to the launch. Cape Canaveral 2011 on Atlas 1. Four rockets, 5 meter diameter fairing at the top, and the curiosity, of course, was within it. So that was a good start. Rocket launches don't always work. And this is where we're heading. This was reflected when Gale Crater. So I don't know. This is a fairly ubiquitous image. It's called the modern image of Mars in 1997. It's a digital elevation model from millions of laser shots taken by the Mars Sample. So we see the ancient highlands mainly in the south and the lower northern lowlands. And the ancient highlands are largely shaped by the phase in the solar system evolution we call the heavy bombardment, or the late heavy bombardment, about 3.9 billion years ago. It's left those large craters. So we see the same effects on the Moon, Mercury, other planetary bodies. Those tended to form and then pretty much just stop, plus or minus a bit of basalt coming through the thick lithosphere. For Mars, and on that, but put aside Earth for a minute, on Mars, these craters, including Gale, were able to trap water and form large and large environments with thick sedimentary successions. Okay, so there we are. There's Gale Crater. Interesting position between the ancient highlands, right on the crustal dichotomy. And there's our traverse. So we landed here. There's our landing ellipse. So 1976 was Viking, the landing ellipse, and the area where you're confident you're going to land was about getting up to 200 miles across. Here we're down to about 20 kilometers. So that radically changes or expands the number of diversity of places that you can visit. Okay, so why Gale Crater? Well, it has 5.5 kilometer high mountain ascent, Mount Sharp. There's our landing ellipse. There's our landing ellipse. And from orbit, we predicted there was an ancient alluvial fan. And importantly, it wasn't just the imagery. The near infrared clay has some very characteristic absorptions of 1.9 and 2.3 microns. So by looking at those, it was predicted, but no one was certain, because we didn't have what we call ground truth, that there would be a lot of clay in the sediments. So we'll see later whether this was or not. Okay, so but then you see the basic idea, the hope is that there's the near infrared with absorptions in which predict clay. But near infrared spectroscopy, the way Mars is, it's rather dusty, so they never encountered for nonetheless, there was our working hypothesis. Okay, so we have the reason we want that large stratigraphy of sediments is we want to see if we can track through the warm and wet time in Mars through today's cold and dry environment. So the idea was we were going to drive through this in our transect, and along the way we'd see mineral assemblages which show different sorts of rock action. Okay, so here is our laboratory, Mars Science Laboratory, and about 1 ton in total. So we have a robotic arm with an X-ray spectrometer on it, drill material, pick it up, carry it within the turret, then move it onto the main body of the rover and drop it in, so we can have this powdered rock for X-ray diffraction and mass spectrometry. Lots of cameras. We have laser as well. We can't really see the laser on Mars, but there it is. We use it's an atomic emission technique. So we create a little plasma spark, and looking at the intensity of the light across different wavelengths, we can calibrate it and work out composition of rock. And I don't know how many millions of laser shots we've taken now, but incredibly, our laser is sort of firing away, and sort of 3 times a week we take out set observation. So that's one of the things I do. Okay, we have mass spectrometers and gas chromatography. So people from a sort of chemical, geochemical background, the technique that you use for isotopes and for identifying organic compounds. Okay, so here's the atomic emission or laser-induced breakdown spectroscopy. So we look from UV just up to the near infrared. We have 3 spectrometers. We take the light, which is detected at the here with this with the ChemCam telescope, and then that signal is fed into the main body of the rover, and the intensity of these beats have been calibrated. So we now have this incredible planetary data set across 12 years. That's one of the things that I've been working on. Okay, so we can normally do up to 10 meters, but these days we would file for that. But the good thing is we don't always have to spend a month in one locality when we're drilling, etc. We can do a quick reconnaissance, which is important, so that we can work out what are the real key targets for this using our mass spectrometer. Okay, it also has the useful effect that the laser blows off the dust on the surface for other instruments. Okay, so as we were preparing for landing, we worked at the Jet Propulsion Laboratory, which is Mars HQ really, in Pasadena, in Los Angeles. And this is our if you like, a sort of a flight spare model. Technically, I think a qualification model for the rover. And that is just about as close as I was allowed to get. Getting close on that, and the engineers will politely but firmly tell you to sort of back off. But as we were using the instruments for the first time, deploying the mast, etc., we had to practice all this in the Mars yard, including drilling, including driving operations. We have now ridden over up 20-degree slopes, etc. So we're starting to use the full capabilities of the rover. Okay, landing night in 2012. So here's the challenge of landing on Mars. Closing velocity is about from what's called a Pullman transfer, or direct transfer from Earth, which the planets in conjunction 26 months, so that becomes possible. That's why you get Mars missions, they tend to be every 26 months. But we've got to go from 7 kilometers per second to rest in about 10 minutes or 7 minutes. And there's some really cool videos out there. I do recommend that. Anyway, everyone was very nervous at this point. It was a new landing system called the Sky Crane system. Here it is. Extraordinary thing, really. Sort of, if you like, classic way of landing, of using an aeroshell to do first set on the main deceleration, then parachute stage. So now you're down to sort of maybe kilometers per second. And then the parachute has slowed it down further. Then there's power descent to the last few tens of meters, and the rover itself was lowered on 3 nylon tethers. So, what could possibly go wrong? And yet it all worked. And 15 minutes after landing, got the signal on the first imagery back. It was great working at Pasadena, so I was able to talk to some of the engineers who built this. They were saying, a lot of the heritage came from helicopter reaching and things like that. And subsequently been used successfully on Mars 2020 as well, and I think we'll be seeing it again. Okay, we used the high-rise camera, remember the 30 centimeter per pixel one, and we were actually able to capture the image of Curiosity coming down to the parachute stage. The power of the joint orbital and lander science capabilities. That's after the aeroshell had just been dropped. We kick up a bit of dust, which turned out to be very useful. And then, hooray! Here were my colleagues on landing night. We just got so I'm very happy. And then on to work. So, in the first 90 calls, we worked on Mars. Mars is at 24 hours, minutes a day, so you very quickly get out of kilter with Earth time. So if you don't work on a transmission, then you'll probably spend half your time, at least in the early phases. You couldn't do it for 12 years, and work in the middle of the night. And some people sort of took this to extremes. And one of my fellow participating scientists actually came to watch which runs at Mars time. So if you should ever see someone associated with a space mission with 2 boxes on, then you know that they're working on a different extraterrestrial time zone. Okay, so we get to work quickly. We come a long way, we don't know how long the rover is going to last. So here was one of our early, really key localities called Young Knight Bay. Some of you may remember, there's quite a lot of media attention on it. From our point of view within the team, this was really important because we've been having these discussions. People who worked on Hawaiian basalts all day. One set of opinions that were saying, look, these layers are just the basalt rock. You can form anything like channels or whatever, People who spent an entire career working on mudstones said, no, these are mudstones. This is what we come for. So it was really only when we got right up close, that close, then there's no more argument. Yes, Mount Sharp is sedimentary rock with these fine-grained mudstones, a great target for. Interestingly, just as an aside, same debate took place with the Sedgwick Mars 2020 landing more recently. But this time it was the other way around. People saying, no, these are all sediments. That's the sun was written. So the upshot of this is even sort of, if you like, fairly basic meat and potatoes stuff that any of you from a sort of geological background might think is obvious. It's actually quite difficult, even with those great instruments, because you're a bit discombobulated and there's dust covering. And so it's actually quite difficult. And that's why you need close-up instrument and a range of techniques to establish these, resolve these debates. Okay, so here's a sort of fast forward to sort of a summary, particularly for people with a sort of sedimentary interest. So we landed first on a sort of series of conglomerates, called the upper patches. The second way we see some of the shallow, rapid, alluvial fans or pebble beds. The projector at that point seems to have switched off. I thought, okay, I'll keep an eye on that from now on. That means I've gone on too long already. HTML. There we go. All right, so I'll keep an eye on it. Right. Okay. Okay, so we started with Rover Prime near the margins of the crater, where we landed. We saw those mudstones, lots of diagenetic features, and we saw these large expanses. So here's a sort of summary. We've got this ancient lake around, we think, from early Hesperian. So we're extending the range of warm and wet Mars into what's called the early Hesperian era. So in other words, sort of 3.5, 3.6 billion years ago. And we have this succession from the conglomerates through into deltaic rocks and mudstones and that sort of distal material. And now we have stratigraphy on Mars. I can go in detail to that on Earth. Usually planetary stratigraphy is necessarily very crude, but we're getting more and more detail. So we've got 400 meters and counting of thickness of mudstone now. Okay, there's some other sort of key things along the way that we analyze, some mudstones, lake beds, and also got some polygonal cracks. So sometimes the lake seems to have desiccated and dried out very soon, and we see that in some of the fracturing patterns. And these, I note these are from the targets show that was 400 meters of kilometers. Then the basin started to warm up, and we see some of these silica-rich fractures, and nodule, raised ridges, etc. So these are great targets for our laser. From the early papers that we wrote were targeting these features, and we found the poly-rich and sometimes silica-rich, etc. So there's been quite a lot going on in terms of water rock reactions as well, and almost ubiquitous, certainly in the lower part of the stratigraphy, these calcium sulfate, gypsum to basanite beads as well. Okay, so this shows why we drilled a successful drilling of Mars. Mars is red. You all know Mars is red. You see it in the night sky sometimes, but red Mars is only about, about that thick. we want to get away from that as far as possible if we want to preserve organics. So you can see some of the testing assemblages. So you can see once we drill, this is about sort of 5 centimeters deep, 1.5 centimeters across. We get into a very different sort of a Mars. So here we were drilling into some of that mudstone because we wanted to do GCMS, mass spectrometry, X-ray diffraction, etc. There's our trusty drill bit, and there's the inlet which we drop material onto. So we're now up to 36 successful drill holes. And it doesn't always work. Sometimes the rock is fractured and the auto safety controls stop drilling, or sometimes it's too hard if there's too much iron oxide in it. But here you see the sort of the variety. The colours reflect the variety of mineralogy. Iron oxide rich zones, we have clay rich zones, some of them more silica rich. So you can see just visually with the different colours, the range of mineral assemblages. So part of the reason for drilling is because we want to do X-ray diffraction to get quantitative mineralogy. So there's the back of the CCD, and the radii of those lines, called the bylines, give us the angle of reflection. So we've got our 2 theta in the Bragg equation, and we've got our wavelength, cobalt 60 source. So we know that, and we can work out the angle of reflection, then we can work out our crystal planes. So when we did that, and we started finding lots of 1 nanometer spacing, which so this is very characteristic of clays or staphenite, which remember are being predicted from orbit. So now we've got a real powerful tool, and we know that our orbital near-infrared predictions of mineralogy are pretty accurate, which is good for planning future missions, future exploration, or understanding the planet, because now we've got the ground truth. Okay, so we're finding lots of clays. So, you know, in some of that, what we call the Mars formation, up to 38%. So again, it's all evidence of this long-standing lacustrine type environment. Lots of debates about whether the clays are detrital or orthogenic, and what's formed in situ as the rocks are buried. But nonetheless, we were able to get to work on them and compare them to our other bit of ground truth from Mars, which are the Martian meteorites. So if you ever come to a talk by me about Mars, then you're quite likely to hear the Mars meteorites. So there you go. I will be monitoring eBay. So the other way we found clay on Mars was by doing mineralogy on some of the Martian meteorites. So we see these these veins of staphenite minerals and serpentine, etc., and carbonate, lots of carbonate. Those are the Martian meteorites. So we've now got this really nice comparison between what we see in our labs on Earth and what we're seeing on Mars. The next stage, just to fast forward to the end of this talk, is a Mars sample return. Bring back selected samples from Mars to compare and do these sort of electromagnetic analysis. So our knowledge of the mineral assemblages associated with water is increasing greatly, and it's stimulating the meteorite work, which in turn feeds back into the Rover mission work. Okay, so what do we think is going on? Well, once you've built up a mineral assemblage and you're confident it's more or less right, then you can start predicting what sort of temperature, sort of pH occurred, etc. So we think a lot of those clays are formed at what are called diagenetic sort of temperatures, so maybe up to 50 degrees centigrade, near neutral pH by relatively dilute brines, plus or minus carbonate. And that was sort of relative used to combine X-ray diffraction with the laser shots to get the composition. So we're starting to work out what that environment was like. This is, I think, a sort of classic image from Liz Rampey, who's now co-PI of Canon Instrument, of the Rover, and it's reversed up mount shot, and we see different haze, so different sulfates, so quite a diversity. Okay, this is just I put this in to highlight. You see, sort of in the middle there, the 2 theta corresponding to iron carbonate. So something we're always looking for in meteorites or Mars. The reason I'm including, I think we've got a visitor here. I know you've got a visitor here called Ben Tutulu, who is also now working on Mars Sample Laboratory, and we're actually working together a bit on carbonate. Why we're interested in carbonate? Because if you've got a carbon dioxide-rich atmosphere and you have water, then you could start conducting or start precipitating carbonate. And that can tell you again about the past environment, atmospheric thickness, etc. Okay, what about organics? Right, so this is a bit of a mixed story. So going back to the Viking era in 1976, lots of controversy, of course, on Mars. But the sort of general assumption is that no organics were detected. But now we have a more powerful set of 2 mass spectrometers and gas chromatography. So here's the inside of the family tonight. It's really almost a mission in its own right. It's also very powerful. So when we switch this on, we can't really do anything else. But that said, we are very powerful. And so maybe if I throw a question at you, so it's always interesting to see what people's take on this is. What do you think the sort of the power rating, the power budget of a rover like Curiosity is? Order of magnitude. What have you got to work with on a space mission? Okay, no wrong answers. Is it megawatts? Sorry. Watts. Yeah. Okay. So it's only 100 watts, which in old terms is like incandescent light bulb. So we've got to drive, we've got to drill, we've got to use all the instruments with our budget from our radioisotope source, plutonium-140, and we do all that at 100 watts. Okay. So anyway, here's the solid inlet. We have gas chromatography, quadrupole mass spectrometer. There's also another mass spectrometer we use for atmospheric analyses. We've got some lots of isotope analyses, including carbon-13 enrichments. The atmosphere of Mars is enriched in heavy isotopes because of all the atmospheric loss processes. But so one of the organics was methane, and we have reported seasonal spikes in methane abundance. When we started off, we found an enormous amount. We found in something like 10 parts per million or even more, which is sort of extraordinary in this context. So we thought we were going to get Nobel Prizes. But life wasn't quite that simple. So we worked out, after we did a few duplicate analyses, that we've got a powerful rover we can do, that most of it was contamination. We brought a little bit of methane with us from Pasadena. But we'll keep on doing them. And we are finding these seasonal abundances. Rather controversial. The Mars Express team are rather skeptical. They're not sure that, or rather, I should say, the twist team with the NOMAD instrument designed to analyze for methane. Haven't identified it, so this is one of the conundrums at the moment. How much methane is there on Mars? So maybe Mars Sample Return will solve it. So methane maybe forms from some sort of relic trapped ancient life which has been preserved, and the methane just stay there, released periodically. Or maybe, of course, you can do it from water. So looks like there's some at least traces of methane, but quite how it formed, of course, we don't know. So we've got pieces of the jigsaw, but we don't quite know how it all formed. Okay, so NOMAD, trace scaffold, one or other missions, no results so far. So one of the puzzles. Okay, I don't know how we're doing for time. Do tell me but for those of you who like igneous rocks, then we have those in Gale Crater as well. So these are some of our igneous rocks, and they're sort of the bona fide ones, which are unambiguously igneous, are notably feldspar. So we've got this new view of differentiation of the Martian lithosphere. So here's an early one, sort of trachybasalts. Again, this was largely using ChemCam data from my PhD students. And then we've got some really cool cumulates, including this one, which we published last year with John Barron, called Askerbol. So we named this after, well, Helen Williams will know about Askerbol. It's a classic calcium mountain on rum. Here we've got these very feldspar-rich cumulates, possibly with alcohol as well, which is unusual for Mars. So we're finding some new sets of igneous rocks, not just fine-grained basalts. These are some form of cumulate, plus or minus alteration, overprint, and it has been argued that these may be a sign of an early primary crust. A bit analogous on the Moon, where you see the North Pacific Highlands, the Perth Highlands. When you look at the Moon, that's the early primary crust from flotation of low-density minerals. Maybe it has been argued there's something similar on Mars as well. How do these get into a great big sedimentary pile? Well, that's an interesting question, but somehow they're brought in, I suppose, from down those little rivers and the pebble beds down into Gale Crater. Okay, I think in the interest of time, I won't dwell on this too much, but the good thing is we can use the data in a sort of traditional way, in a sort of similar way that you might use on Earth. So we're looking for those analogs on Earth to understand this. So some of you will recognize sort of classic total alkalis against silica, or against silica, etc. Classify these rocks. Better understand. Okay, related to this, with Anders Bedford, one of our ex-PhD students who is now working on a research mission and she's also working on Mars 2020. I recommend inviting her to give a talk. Come across that. So one of the things we can do with sediments, if we're really careful to strip out the alteration effects and side filtering effects, is that you're left with the detrital mineral signature. So in other words, what the material was that was being brought in from the source. And when we look at that, we find, you see, that we've got quite a large range in silica and alkalis, for instance, and other major elements. So what this is pointing towards, at least qualitatively or approximately, is that the source composition of the igneous crust, which was being eroded and fed into the Gale Lake, was quite fractionated, quite a large variation. It wasn't just a primitive sort of basalt of 40-odd weight percent or something like that. There's a lot more going on in the Mars crust from an igneous point of view, as well as the sedimentary which was the prime reason for going to Gale. Okay, yeah. So we published that in Maps a couple of years ago. Oh, 15 minutes, okay. Well, I will note that one of the great things about going to Mars is it's a really good place for finding meteorites. It's just about the best place in the solar system. meteorite because it's cold and it's dry. So every now and again, we just see something like that. Just this lump of meteorite lying there. So we have this, as we've done, here's our traverse. And along the way, we found lots and lots of iron meteorites. So we sort of get a sort of almost an added bonus. You know, it's not why you go to another planet, I suppose, unless they're sitting there. So any of you who are interested in meteorites can maybe see some of these and some aeolian scouring for these little meteorites. So, yeah. And yeah, so there's an example of our atomic emission, laser-induced breakdown. So we see nickel and iron, just as you would. No doubt you've got some iron meteorites in your collections here. We also see lots of sand dunes, and in fact, we spent really basically the first 2 years going around these dunes called the Bagnall dunes, these small barkens, and we certainly don't want to get trapped in them. So we have to be very careful about how we traverse these. We have found, for the first time, these are dynamic dunes that move maybe up to 4 meters per year. Okay, into some Glen Torridon. One of the things, one of my sort of rover community duty things was sorting out naming of rocks for a couple of years. So we put it in the Scottish Board, and so we have all sorts of Scottish names, which is nice. Going back to almost the roots of geology. Okay, sometimes we will spend maybe a month or more. If we think of the locality, it's got lots of good things for drilling, etc. Here we see some of those lake mudstones. And then here, if it's going to work, sometimes when we're in conjunction and we can't communicate with the rover every 2 years, we have a sort of a holiday, but nonetheless, the rover can be quietly taking its own images. So here's a nice night day image, if it's going to work, in a place called Geddisbauer. So this is our route up Mount Sharp. You see those, we're in basically a canyon. So it was great, all sorts of features, textures, etc., to keep the physical sedimentologists happy. Okay. But curiosity is mortal. We have been puncturing holes, especially in the first part of the mission when we didn't really know what we were doing when we were driving. Some of these rather thin aluminium wheels got holes in them. So sooner or later something's going to drop off. Circuit board will break that. You know, so far it's still going. Okay, this all feeds into future work. ExoMars now, we hope 2028. So large part of our landing site selection has been informed by the ground proof from Mars Science Laboratory. So we'd like for ExoMars to go back to something pretty similar to some of those sheepbed mudstones we need to drill on ExoMars. Mars 2020 and Mars Sample Return. So another deltaic deposit in Jezero, but with also igneous rocks as well. So we've had the predictive tool from orbit with near infrared spectrometry and imaging. Gale Crater gave us confidence that this was the right way to do it. That we could predict what the landing site was going to be like accurately. So we've now got a cache of these drill tubes, and one of the things I'm working on, and indeed I'm going to Johnson Space Center in a week's time to discuss how we're going to analyze these as one of the igneous rocks. And so as I say, I think one of the things I enjoy about work like this is what brings you back to roots. So one of the analogues for the Satar formation in Mars 2020, we think maybe the British Tertiary Volcanic Province. And so Helen Williams and I and others went there last summer and collected some of those analogues for Mars 2020. Okay, so, and it has to be said, Mars is of perennial fascination for the wider community, which is good news for all of us. So this was the cartoonist on BBC Scotland take on it. About 2018, they were interested in all these Scottish Mars names appearing. So what have we found? Well, we've definitely found a fluvial crystalline system. There's no ambiguity about that anymore. We've still extensive differentiation, perhaps traces of a primary crust from the igneous rocks. We found organics, benzene, maybe methane. If you put all these together and the mineral assemblage, the clays, show water rock reactions at relatively low temperatures, this was a habitable Mars. If you'd been micro there 3.7 or so billion years ago, you would have been quite happy inhabiting that environment. Whether there were any, was inhabited, we don't know. So the Mars Sample Return future missions the way. We're now moving into the colder, more desiccated environment, sulfur unit towards the top of chart as we go up against Spallis. So we're moving over an important transition. So stay tuned for the results over the next few years. Okay, so probably talked for a bit too long, but there you go. Okay, so back to you.
Any questions?
Professor, I have two questions. First might be a serious one. When you send the curiosity rover on Mars, you sterilize the rover so that you don't bring any chemical or bioorganic contaminations to Mars.
Yeah, it is in effect it is sterilized and clean. Practice that comes down to a certain number of microbes or something like that. But yeah, there are very stringent what we call planetary protection controls on sending material to the back. So yeah, it's a major concern.
The second question is on this slide, you mentioned that we are greater than 400 meters thickness of Mars. Obviously, you cannot drill that deep on Mars. So how do you estimate?
Well, we've been going up the steps, the stratigraphy. So the stratigraphy is the treatment of the stratigraphic column. So it's I think, well, there are two different ways of looking at the stratigraphy, but the main way is just a sort of fairly simple layer cake, and we're driving up it. And so we just log very carefully every day. We know precisely where we are, how far we've gone, our elevation. So that's how we look.
Thank you. Thank you.
Wow. Well, almost all of them have been incredibly successful. With my ChemCam hat on, I probably ought to say ChemCam, but I couldn't not say. So it has to be a draw between ChemCam, X-ray diffraction, and all those chemical, which is extraordinary, really. And then there's the X-ray spectrometer, which I didn't even mention. Then there are the cameras, multispectral cameras. If you don't have those, you can't do anything. But so there's a lot. And that's not even taking into account the engineering. So the drill works, it broke, and then the engineers will have to fix it. I'm not trying to discuss that, but it's not a sort of static mission and then you just turn on the ignition and that's it. You have to problem solve, change, recalibrate, etc. So actually, I can't answer your question because there are too many of them. Okay.
So since you are there in Pasadena with all the engineers, I was wondering, do you know what usually the required career path for an engineer to get into this project?
Pretty diverse, actually. So sort of range of different backgrounds. So there are people who go from, sort of physical science backgrounds, maybe work using intern at JPL or something like that. We see that sort of group quite a lot. Then there are people, people from universities. Broadly, it's not, JPL isn't the only player in town. There are other large labs. There's John Hopkins, there's Swirly. So, although JPL is very high profile, largely because it's got Mars portfolios. There are, of course, lots of other organizations, an increasing number, and commercial small entrants as well. So, but yeah, mechanical engineers, electrical engineers, thermal engineers, systems engineers, etc. There's lots of sort of different specialities in terms of engineering, in terms of physics, geology, chemistry, etc.
First of all, where have the avenues that experience, curiosity and maybe also perseverance had to mix, where because you had such a specific objective, you had to abandon some possible roads that you could have taken?
Yeah.
You know, what kind of task? So what would we learn about geology from just looking at this kind of very narrow view? How does it change the kind of, did we change an approach? A lot of it was planned, but some of it was then the approaches that you take, distinguish between the massive and maxstone, and distinguish what has happened. We probably learned something from these devices. And is there something that's going to change with it? Let's say the ingenuity now taking this big scale picture. Can we learn geological approach? So it is not to be like
Well, we have a lot of work goes into planning the main route, okay, from a landing site up to getting started. So we have to select where we can go. We're pretty confident we're not going to get stuck. Balance with the science. So yes, so there's a lot of discussion of that, and there is that balance between acceptability and science. I think we made a pretty good selection of what's called the MSR route. New technology will come along, so the Ingenuity helicopter, yeah, probably be seeing those again in the next stage of Mars Sample Return. So, but it's about having the different instruments working together, complementary data. So, if you have some cameras, that's okay, but it's when you combine that with the X-ray diffraction and the laser, etc. That's where you get the complementary data sets. Does that sort of answer your question?
Yeah, so is there something that, because the thing that ingenuity is, then we need to set engineering prototype, or have
Ingenuity.
maybe actually learn something from surveying up close?
Oh yeah, so that helps you decide where to go to drill. So yeah.
But on its own, it doesn't tell you much about the way you can see for something.
I don't know, you'd have to talk to someone on the Ingenuity team. They would probably beg to differ.
Question about the mine students. You mentioned that curiosity is mortal and there's potential damage to the environment on Mars, and it has a very different like environment, like air, fire and stuff. What specific design made to protect curiosity from such hazards?
Well, it was very the Mars 2020 was I suppose the main difference this rover is that it has stronger titanium wheels. So that's quite thin standard aluminum plate, which we now know isn't really quite strong enough. So that was one quick solution for that. But it has to be said, you know, the electronics boards are still working. There have been problems with the some of the computer software, but we have a sort of redundancy built in. So it's one part of the software starts causing problems, we can use a different sort of part of the computer system, and then we can do a workaround. Computer scientists to do a workaround. So we've got redundancy built into the system as well. So we want to minimize as far as possible the single point failures. And I think that's been quite successful. Also, you've got to do a lot of problem solving as you go along. You go back to the qualification model and work out how to use your drill in a different way, and things like that. It's quite a sort of dynamic process.
Here's about our national population rate
battery exploration missions, because if I'm not mistaken, the Mars Sample Return mission was solely done by NASA. It was not like the NASA-ESA Mars like witnessing, like, for example, you were talking about many non-American universities and institutions also collaborate on. I'm just curious as to how that works, especially from it's
Well, NASA, although it's the sort of got largest, even NASA can't afford to do everything itself. One thing. Also, it wants to work with the international community, so it puts out students for participating scientists. Which is how I initially joined. But the ChemCam instrument was for part French Iraq lab in Toulouse and part Lanel once with more in Mexico. So that was a key international collaboration. So NASA didn't have to pay for everything, and also to get the expertise from the other international labs. So it works very well for NASA. So where it can fall down is in extreme environments. Say you've got so they are not a reliable partner anymore, so that's where XMR's got into big trouble. So it can cause problems, but we hope to find a way forward. And NASA are generally pretty committed, with a few ups and downs, to working with European Space Agency. We hope so. For XMR's sake.
Very interesting thought. You mentioned sample return when you're working on the plants. What's happening? Because I've heard stories that it's expensive and blah, blah, blah.
It's certainly JPL have the Mars portfolio, but it comes with a cost. So again, it's not uncommon for space missions to go well over budgets and be delayed in space shuttle, for instance. So I think one of the reasons these are playing a major part in this is that NASA don't really want to try and do it all on their own. So these will be providing some of the key components like some of the ground-based work. Yes, definitely is. So one of the things with my left hat on that we're developing are some of the isolator cabinets, new types of those to house samples when they come back. So we're going to sort of go to what we are going to in a few weeks. We're going to try and sell it to them, basically. But I think that's one of the ways Europe and the UK will be involved in Mars Sample Return.
Have any studies been done on how long the excavated mudstone in drill sites stays life chain colored?
Well, the reddish colour is because of ferric oxide. It's an oxidizing sort of environment. So when you go just below the surface, then you don't have that same intense oxidation. So the clays are preserved rather than being turned into iron oxides, etc. So that's why we're drilling with Mars 2020 as well. That's why we want to drill with X and get below the surface.
was about in the slow process of 2D drills.
Oh, when you drill slowly, because if you drill quickly, then you start heating up. Generally, you do everything slowly.
The oxidation.
The oxidation has had billions of years. So the sort of landscapes we see now are certainly hundreds of millions of years old, basically. It's been plenty of time for the surface anyway to oxidize.